Okay, so we are ready. Let me share my screen. Can you confirm that? Can anyone confirm that screen is visible?
Yes, sir.
Okay, thank you. So, good afternoon. This is third lecture on cryptography. As you know that first lecture was an overview, what we are going to do in the course and some historical things. Second lecture, we started with this modular arithmetic and finite fields especially. So those who have done discrete mathematics with me, they may know that we have already done these things earlier. But just to recapture and recall, because these things are very important for certain cryptographic applications. Okay, and one more thing. So last time I think somebody asked me a question about field with 4 number of elements. That how 1 plus alpha is same thing as minus 1 plus alpha. So I'll just again recall few things, and from there we'll take it further. Okay, so we are looking at classical cryptography, and in the classical cryptography section, I have to tell you how certain ciphers are done. Okay, so we were looking at this, as I mentioned, finite fields, and finite fields are quite useful for AES advanced encryption standards or elliptic curve crypto systems and so on. So just to recall how we constructed complex numbers, field of complex numbers from the field of real numbers. We look at a equation x square plus 1 is equal to 0, and in the ground field, if there is no root, we attach root I and extend real to get complex, like a plus ib, where a and b are reals, and I is the root of the equation x square plus 1 is equal to 0, which is I square plus 1 is equal to 0. That means I is equal to square root of minus 1. So there is no real. So square root of minus 1 does not lie on the real line, right? So it is an imaginary number. Okay. In the same manner, in analogous way, we looked at the ground field Z2 is equal to 0, 1, which is a field with 2 number of elements, right? And we added alpha. Alpha is an element. So we look at couple of equations, and we found that equation x square plus x plus 1 is equal to 0 is a degree 2 equation over the ground field, which has no root. Just like that, x square plus 1 is equal to 0 has no root in reals. X square plus x plus 1 is equal to 0 has no root on Z2, because if you put x equal to 0, this is not a solution. If you put x equal to 1, this is not a solution, right? So that means this polynomial or this equation is not solvable over Z2. I call alpha as a root of this equation, and I attach a plus alpha b, where a and b belongs to Z2, and the equation is alpha square plus alpha plus 1 is equal to 0. Here it was I square plus 1 is equal to 0. Here it is alpha square plus alpha plus 1 is equal to 0. So we have done this construction. We saw, so some of these things, let me recall again. Okay. So we have field with Galois field with 4 number of element as a plus alpha b, such that a and b are in Z2, right? And we have the equation that alpha square plus alpha plus 1 is equal to. Now people are asking a question, how come it is possible that alpha square is equal to, so we know that this is okay, but from here how come alpha, this thing is equal to alpha plus 1? This confusion is still there. So just observe that every element, so let me write down all the elements here, so then it will be clear. 0, I am writing all the possibilities of a and b, 0, 1, alpha, and 1 plus alpha, right? Now when we are adding any of two these elements, so now what happens? because these coefficients a and b of this polynomial are in Z2. Z2 means field with two number of elements where we know that 1 plus 1 is equal to 0. So that means 1 is same thing as minus 1, right? So the same thing is happening here. You see that here I can write it down. Alpha square is equal to minus alpha minus 1, right? Now minus 1 into alpha, right? Minus 1, this can be written as minus 1 into alpha, okay? And minus 1. Now this minus 1 and this minus 1 belongs to Z2, right? They belongs to Z2. So Z2 we know that 1 is same thing as minus 1. That means this is nothing but alpha plus 1. Okay, so alpha square is equal to alpha plus 1 because coefficients are in Z2. We are always handling. So if I say alpha plus 1 plus alpha, I am adding these two elements, say this and this. So what is happening? This is 1 plus 2 alpha. Now this, as soon as the coefficient is 2, we know that in Z2 2 is 0. 2 is nothing but 0, right? So this is nothing but 1. When we are adding two elements, we are getting 1. So I hope this clarifies the doubt that how this thing is handled, right? So that's, as you can see here, 2 alpha is equal to 0, 2 is equal to 0, 2 alpha square is equal to 0, and so on, right? So this is how we, and also note that alpha cube turns out to be 1 because alpha cube is equal to alpha into alpha square, which is same thing as alpha times alpha plus 1 because alpha square is nothing but alpha plus 1, which is alpha square plus alpha, but alpha square plus alpha from here is minus 1, which is same thing as plus 1. Okay, so alpha cube is equal to 1. So alpha is a cube root of unity, but it is not a complex cube root of unity. You need to remember that. Okay, it's a cube root of unity, but it is not a complex cube root of unity. Okay, so I think if I want to extend this, if I want to go into field with 8 number of elements, so what I do here, I look at 2 cube. Okay, so I need to look at Z2, and over Z2 I look at degree 3 because this number here tells me what degree we should look at. So I can look at ax cube plus bx square plus cx, okay, plus d equal to 0, where a is not equal to 0 and a, b, c and d belongs to C2. Clearly you can see that a is not equal to 0, so equation is x cube, a will be 1 in that case. It is x cube plus bx square plus cx plus d is equal to 0. How many equations are possible now? 2 choices here, 2 choices here, 2 choices here. Total 8 possibilities are there. So can anyone tell me, I think it is a good exercise, what are the equations which are not solvable over Z2 out of these 8 equations? So I can write down some of them. Maybe x cube plus x square plus x plus 1 is equal to 0, right? X cube is equal to 0. X cube plus x square is equal to 0, right? X cube plus x square plus x is equal to 0, right? Then x cube plus x plus 1 is equal to 0. X cube plus x square plus 1 is equal to 0. 1, 2, 3, 4, 5, 6. What are the two more? What are the two more equations? Anyone can unmute and answer. Yes. Anyone?
X cube plus 1 is equal to 0.
X cube plus 1 is equal to 0. Correct. And one more, right?
X cube plus x is equal to 0.
X cube plus x is equal to 0. Very good. Now, out of these 8 equations, tell me which one has no root over Z2. What about this equation? Clearly x equal to 1 is a solution here, right? If you put x equal to 1, 1 plus 1 plus 1 plus 1, modulo 2 it is 0, right? So this equation is not going to work for us. What about this? X equal to 0 is a solution, so this is also not going to work. What about this? X equal to 0 is a solution, so this is also not going to work. X equal to 0 is a solution, so this is also not going to work. What about here? X equal to 1 is a solution, so this is also not going to work. And if you put x equal to 0, this is also is a solution, so this is also not going to work. Now if you look at x cube plus x plus 1, if you put x equal to 0, no solution. X equal to 1, 1 plus 1 plus 1 modulo 2 is 1, which is not equal to 0. So this has no solution. This is going to work. Similarly, this equation x cube plus x square plus 1 is equal to 0 has no solution over Z2. So this is going to work. Now we have got two equations, right? In order to construct field with 8 number of elements, either I can take this or this. It doesn't matter. So I will, if I take x cube plus x plus 1 is equal to 0, our field, we can write down the field with 8 number of element as A plus alpha B plus alpha square C, such that A, B, C belongs to Z2, right? And where alpha cube plus alpha plus 1 is equal to 0, right? So we have all the 8 elements as 0, 1, alpha, alpha square, alpha cube, alpha raised to power 4. Can you tell me which power of alpha will be 1? Anyone can unmute and answer. So you just remember here in ZF4, we know that alpha cube turns out to be alpha into alpha square is equal to alpha times alpha plus 1 is equal to alpha square is equal to 1. So alpha cube turns out to be 1, right? So I can say that the elements of the field are 0, 1, alpha, alpha square. 1 plus alpha can be written as alpha square, right? So it's the same thing as this. So this goes up to 0, 1, alpha is power 0, alpha is power 1, alpha is power 2, right? 1, 2, 3, 4. So I hope you're getting an idea. In case of 8, how many will be there?
So alpha to the power 7 will be 0. 1.
You want to say alpha raised to power 7? Let us compute. Alpha
Yeah.
raised to power 7 will be what?
Alpha to the power 6 into alpha.
Alpha into alpha raised to power 6, which is nothing but alpha into alpha raised to power 6. We can write down as alpha cube square, which is fine. Now it is alpha. Alpha cube I can put from value from here, alpha plus 1 whole square is equal to alpha into alpha square plus alpha. Note that if you expand this, 2 alpha will come, right? But 2 alpha will be 0 because modulo 2 will be 0, right? We are left with this. This is nothing but alpha cube plus alpha. Alpha cube plus alpha. Now from here, alpha cube plus alpha is equal to 1. So this is 1. Very good. So here the power of alpha will go up to what?
6.
Alpha 5, alpha 6. 1, 2, 3, 4, 5, 6, 7, 8. All 8 elements. So T time, make these tables, which we have done it for GF4. Make these tables, 0, 1, alpha, alpha square, alpha cube, alpha raised to 4, alpha raised to 5, alpha raised to 6. And here 0, 1, 2, and so on, right? 1 minute. Right, so like we can make tables for addition. Similarly, we can make table for multiplication. 0, 1, alpha, alpha square, and so on. I think today in the evening tea time, you may try to make this table just like that. We have done it for GF4 here. We have made table for GF4 like this and this, just to make sure that that whatever we have constructed is a field, right? Field with 8 number of elements. Now, one thing you might have noticed, in case of GF4, we had only one polynomial, one equation which has no root, which is x cube plus x plus 1 is equal to 0. Whereas in case of field with 8 number of elements, we have got two equations here. So I have constructed field using this. What will happen if we take this? Any idea? Any one can unmute and answer. What will happen if we take x cube plus x squared plus 1 is equal to 0? Are we getting two fields with 8 number of elements? If we take the second equation, x cube plus x squared plus 1 is equal to 0. So what happens if you take the other equation? Then also you get field with 8 number of elements, and actually you can just swap the field. Both fields are isomorphic. If you might have heard this term isomorphic, okay. So whatever construction you get only one field actually, no matter which polynomial you take. So this is an important thing to observe. If you take the other equation, x cube plus x square plus 1 is equal to 0, that means alpha is the root of the equation this, that means alpha cube plus alpha square plus 1 is equal to 0. And in that case, you try to construct the field with 8 number of elements, you will get same thing, right? So basically one may ask this question, so this was we constructed field with, I think if I ask you, so we constructed field with two number of elements, 3, 4, 5, 6, 7, 8. What about 9? 10 is not possible. 11, right? So what about 9? How will you construct field with 9 number of elements? So I'll just throw some light here. This should be Galois field 3 square, right? So what I do, I take a field with 3 number of elements, which is integer modulo 3, 0, 1, 2, right? And I take equation of degree 2. So that means ax square plus bx plus c is equal to 0, where a is not equal to 0, but a, b, c belongs to D3. Note that this 2 is same thing as this degree 2. That we need to keep in mind. So now again there will be certain number of equations. How many equations will be there? 3 into 3, 9 into 2, 18 equations will be there. Out of that we need to see which one is irreducible, having no root over ground field, and try to construct the field. So in that case, this will be something like a plus alpha b, such that a b belongs to G3, and alpha is root of an equation of degree 2 over Z3, which has no root over Z3. So remember, root of an equation of degree 2, so I can call it, say, fx, right? Fx is a equation of degree 2 over Z3, which has no root over Z3. So f of 0 is not equal to 0, f of 1 is not equal to 0, f of 2 is not equal to 0, right? No root. Then we call alpha as a root of it, and then we extend it, right? This is how we do GF9. Okay. Any question at this point? Please do ask me. Unmute yourself and ask me the question. Any question?
Will be 6 included in the field?
Oh, yes, you are right. 6, there is no field with 6 number of elements. Very good observation. So 6 is not there. I just wrote it. So 2, 3, 4. So actually what happens, there are certain things. Vn is a field, we know, if and only if n is a prime number, right? That we know, right? Now one can ask, what are the forms of the field? So actually we can construct it like this: tower of a field, GF2, field with 2 number of elements, can be extended to GF2 square, right, which we saw. This can be extended into GF2 cube and so on. Finally we can go up to GF2 raised to power m. Okay, so this is known as tower of binary fields. Okay, these are all binary because the ground field is binary, so everything is extension of binary field, right? So this can be nothing but something like a0 plus a1 alpha plus a2 alpha square dot 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 a m minus 1 alpha raised for m minus 1, right, where ai's belongs to g2. Okay, something like this, and where alpha is a root, where f of alpha is 0, fx is a degree m irreducible polynomial over z2. Got it? So this is how you construct. So in other words, in general, we can write all the elements as 0, 1, alpha, alpha square. Alpha power will go up to what? Anyone? Right? So these are the powers of alpha. That is how you can form the field with 2 raised for m number of elements. Now this is the case for binary. What happens if you go for other ones? So suddenly there is a field with 2 number of elements, power of 2, right? 2 square, 2 cube, 2 raised power 4 and so on, field with 16 number of elements. So one can in general say that, in general we can say that ground field is EP, where P is a prime number, and then from there we go to GFP square, GFP cube, field with P cube number of elements, P raised to power m, and we write it down roughly as Q. So a field with Q number of elements exist if and only if Q is a prime power. P is a prime. Okay, so if and only if Q is a prime power. So that means when we go here 11, so all in general we can say that when there is a field in the same fashion, actually, so this field can be written as 0, 1, alpha, alpha square and so on, alpha raised for p raised for m minus 2, right, in general. Okay, so this is how the field with where alpha is the root of a equation fx is a degree m equation which is irreducible, means have no roots in CP. Okay, and that's how we construct. Any question at this point? So I hope you got a general idea about finite field with Q number of elements. Any question at this point? Please unmute and ask.
Hello, sir.
Yes.
Yeah, so how means can we prove that the last element is alpha power p raised to m minus 2?
Yeah, so when you do the calculations, you will see. So basically, you look at the equation. So you need to show that. So what will happen basically is a certain alpha raised to power. So as you know that in case of field with 4 number of elements, right? Alpha cube was 1, right? Alpha cube was 1. In case of Galois field with 8 number of elements, alpha raised to 7 was 1, right? You see that?
Yes, sir. Yeah.
Right, from here you can guess. So you need to compute this thing and to make sure that after that you get 1 itself. Okay. Okay.
Okay.
So basically what I'm saying that you need to you know, I would suggest try to do certain examples like in this case you look at the other, in case of field with 8 number of elements, also look at the polynomial alpha cube plus alpha square plus 1 is equal to 0 and try to complete the example. In case of GF9, you know, try to find out the equation here and see you get the similar results, right? Here this also will be power of alpha. You can write down everything like that, right? And in case of binary, so I would give you as an exercise for field with 16 number of elements. That is 2 raised to 4. The polynomial you can take is x raised to 4 plus x plus 1 is equal to 0. This will work. Okay. So alpha raised to 4 plus alpha plus 1 is equal to 0. So of course you need to look at degree 4 equations and see which one is irreducible. Irreducible means which has no root in the ground field, and then try to construct it, right? So that is how you need to do. So do this exercise to make sure that you see how this is how it is growing right now. I think that much is enough for you. You don't have to go into too much deep mathematics, but at least you, it will convince you that this is how it is coming. Okay.
Okay, sir. Thank you.
Yeah. Any more question? It's good if you ask questions, because then I, you know, then I think that you are understanding it. Yes. So there are a couple of t time problems. You know, as I mentioned, you need to, what are the t time problems? First, you need to look at second equation and work out the field with 8 number of elements and this equation and make the tables. Make the tables, you know. Tables of addition and multiplication. That is an exercise 1. Then I have asked you to construct field with 9 number of elements. This is again an exercise for you, right? Construct a field with 8 number of elements. I gave you the idea. Now you have to work out. You look at this equation over Z3 and try to construct the field. This is also very good exercise for you to understand what is happening. Then this is fine. I mean, then another exercise is field with 16 number of elements. So 8 number of elements, you have to work out the tables. Also tables also you need to work out here also in case of GF16, right? And also in case of GF9 you have to make tables of addition and multiplication for GF9. Okay, once you do this much exercise, I would say that you are ready. You understand the basic idea about finite fields. Then we can actually, you know, talk about a couple of things when we look at the encryption, like AES. I think the first encounter you will have is advanced encryption standard, AES. Okay. Okay. Any more question? If there is any question, please ask. Otherwise, we can go to the next step. I hope you understand now why -1 is same thing as +1, because ground field is Z2, right? Okay, so if there are no more questions, now we start.
Hello, sir.
Yes, please
Sir,
go ahead.
at previous slide, we have find Kalba field of p to the power m. So
Yeah.
their roots are 0, 1, 2, 3 up to p minus 1 are also included in in this GF of Q?
Yeah, so these are actually, yes, you are right, these are roots of this, but actually they are in extension field, they are not in the ground field, they are not in ZP. There is no root of fx. Okay.
Yes, sir.
Yeah, so ground field there is no root. In fact, later on I will show you sometime the factorization. This is a beautiful way of you can factorize the things and so on, factorize the polynomials. But anyway, whenever we need it, we can cover it up. I have given you basic understanding. Okay. Okay, so now the time is to look at classical cryptography. Okay. First, I will give you a formal definition of crypto system. As you know, in the first lecture, I talked about certain, certain ciphers which were used for the English alphabets. But there is a formal way we can define them. So I'm defining in a formal way, and then I'm giving you a couple of examples like shift cipher, hill cipher, and so on. Affine cipher. So a crypto system is a 5-tuple system: P, C, K, E, and D. What is P? Okay. What is P? P is a finite set of possible plain text. Okay. Less than infinity means finite. I'm just writing shorthand, P is less than infinity means finite. Of course, this means finite. Finite set of possible plain text. Okay. C is finite set of possible cipher text. So whatever we encode, so if there is English language, English sentence is there, that is normally plain text. When we encode it, we get cipher text. That is known as cipher text. Then for this encoding we use key. So K is a key space. So it is a finite set of possible keys. Okay. In fact, the next statement is that for every K in key space, for every key in the key space, there exists encryption rule, EK in E, and a corresponding decryption rule. Encryption rule, of course, there has to be encryption rule, and a decryption rule in D. So these are something like functions. I can say that EK is a function from P to C. So it is taking plain text and giving a cipher text, right? It's a function. And DK is a function from C to P. It is taking ciphertext and giving us plain text, such that there is a condition that dk of ek of x is equal to x for every x in P. So that means whenever we take a plain text, we apply encryption rule, and then we apply decryption rule, we get the same text, right? If this is not true, then of course it will be difficult to do encryption decryption. This condition should be true all the time, right? So x is a plain text. Okay, x is a plain text. Let me give you some examples. Okay, so basically a crypto system consisting of 5 items. First, it's a 5 tuple system, a finite set of possible plain text, a finite set of possible ciphertext, a key space, that means a set of possible keys, and for every key there is encryption rule and decryption rule. Encryption and decryption rules are functions from plain text. Encryption rule is a function from plain text space to ciphertext space, and decryption rule is a function from ciphertext space to the plain text space, right? And they satisfy this condition that dk of ek of x is x for every plain text x. Okay, now also one more thing, for every xi in p, plain text in p, we assume that whole plain text we divide it into a string. Okay, and so yi is nothing but ek of xi. Apply encryption rule on each xi part. Okay, for 1 less than equal to I less than equal to n. So our y is nothing but y1, y2, yn. This is how we do the encryption and decryption. Okay. One more thing, if p is equal to c, so in that case encryption function is a permutation. Obviously, because now plain text and ciphertext are same, so we are applying a rule which is giving us the same thing inside the set, right? So first example that we are going to do is the first example, shift cipher. I think this also we have covered in our discrete math course if you have done, but now in a different bottleneck. Okay, so our p is equal to c is equal to k is equal to c6 integer modulo 26, which is a ring, right? Now for every small k less than equal to 25, define ek of x is equal to x plus k mod 26 encryption rule, and decryption rule dk of x, dk of y actually, because y is a ciphertext, is equal to y minus k mod 26 for every x comma y in D26. This is our shift cipher. What we are doing, we are shifting it by certain number of places. So first of all, so what we do, we can write down A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. So we can write down as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So this is the basic encoding that we will always use between alphabet and these numbers. Okay, and so that's how we get integer modulo 26. Okay, so I think let us in this cipher, let us look at an example. We will meet, suppose plain text is, I am actually assuming that there is no space here right now for the simplicity. We will meet at midnight. Okay, and suppose k is equal to 11, the key is 11. So we know that our encoding will be w is what? You can see w is 22 here. W is 22 here, right? E is what? 4 here, 4. So like that, I can just write down 22, 4, 22, 8, 11, 11, 12, 4, 4, 19. Right? And then 0, 19, 12, 8, 3, 13, 8, 6, 7, 19. All things we have written numerically. Right? Now we add 11 to each and reduce modulo 16. Means we divide it by 26, modulo 26. We divide it by 26 and look at the possible remainder. So this will be, if we add here, it will be 33. Modulo 26, this is nothing but 7. 7, 15, 7, 19, 22, 22, 23, 15, 15, 4. Then 11, 4, 23, 19, 14, 24, 19, 17, 18, 4. Now we convert it back to alphabets. We get H, P, H, T, W, W, X, P, P, E, L, E, X, P, O, Y, T, K, S, E. Note that when we look at plain text, normally there is a convention that we write in small letters, and in encrypted text we write, the ciphertext we write in a block, big letters. And actually in some books you will see that plain text is in block letters and ciphertext is in small letters. So I think that is a convention, but we are using it. Plain text is in small alphabets and ciphertext is in big alphabet, right? So now if you want to get the original thing, what we need to do, we need to just convert from here to here and then subtract 11, and we get this, and then we'll convert it, right? This is how we decoding will be there, right? Now the question is, this much you know from your discrete math class. Question is, suppose I give you this. Now please answer. I think if you want a successful career in cryptography, this is a question that you need to answer me. From this ciphertext, what are the ways that you can get this plain text? Please answer, unmute and answer me. What we should do? Any idea? So I'm saying that I'm now doing cryptanalysis. I'm trying to break the cipher. I have the ciphertext in my hand. How do I do breaking of the system?
Sir, we can try different values of k till it makes sense, like from 0 to 26.
Correct. We can try different values of k. Actually, that is known as exhaustive key search. Exhaustive key search. Exhaustive key search. Right. So it is known as EKS, exhaustive key search. Right. So you know that here by doing exhaustive key search, we can write a small program right now. I mean, there's no problem. But otherwise, also by hand, also we can break it, right? If we do the exhaustive key search. So the question is, while designing crypto systems, we should make sure that exhaustive key search is infeasible. Okay. There should be so many possibilities of keys that it is difficult for you to do. So for example, in this case, we may try different values of k and see if there is a meaningful sentence coming out of it, right? So as an example or as an exercise, I would like to give you one exercise. This exercise is for breaking the crypto system, right? So encrypted text is J, B, C, R, C, L, Q, R, W, C, R, V, N, B, J, E, N, B, W, R, W, N. So you need to find out find plain text. Okay, so you need to use all sorts of keys, try different keys and see if you can break it. This is an easy exercise for you. I think if you try 13 decryption rules, maybe 26 by 2, you will be able to break the system. It's very easy. So just try, different keys one by one systematically and find out the plain text. This is an exercise for you as a cryptographer. This is your first task to find out what is the key. Okay, so actually in most of the crypto systems that we design, most of the cipher systems, this is our task. So in our discrete math class, I have not done any cryptanalysis for you. I just did the encoding decoding, and I'll show you how to plain text is encrypted into cipher text and so on for a couple of ciphers. For example, Caesar cipher, I think we have done, right? And a fine cipher also we have done in discrete math class. But here what happens, we are always looking for cryptanalysis. Cryptanalysis means ways to break the cipher. We are doing all the analysis how we can break the cipher. And there are different ways we can attack, so different kind of possible attacks, and that is the real thing. Whenever we are proposing a new cipher or new crypto system, we want to make sure that there are no possible attacks, or this exhaustive key search is infeasible in practice. It is kind of very difficult, and then of course our system is secure. Okay, so let us look at another cipher, which is substitution cipher. Substitution cipher. So again, P is equal to C is equal to Z26, and suppose K is all possible permutations. Right, the key space of 26 symbols, right? So for each pi, for every pi in K, every permutation, this is a symbol for permutation. Okay, define E pi of x as pi of x, apply the permutation, and d pi of y is equal to inverse permutation. So pi inverse is inverse permutation. Okay, so again, as an exercise, as a small example I should do in front of you, so that it's not very difficult actually. Example here. For a random permutation, pi. So suppose again I am writing small alphabets as something like this: A, B, C, D, E, F, G, H, I, J, K, L, M, N, P, Q, R, S, T, U, V, W, X, Y, Z. These are the small alphabets, right? And so these are the, I think, plain text you can say. I'm applying permutation like X, N, capital Y, A, H, P, O, G, Z, Q, W, B, P, S, F, L, R, C, V, M, U, E, K, J, D, capital I. So given the alphabet like this, we have just done the random permutation, you know, and after permutation I have written the capital letters so that we know that which was what, you know. This implies that e pi of A is actually x, A is mapped to x, e pi of B is capital N, etc. Right? You can check that. Now decryption is inverse permutation. Decryption. This was encryption. Decryption is A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z, capital, all capital letters, which are encrypted ones, or it is ciphertext. Now you can say that D, L, R, Y, V, O, H, E, Z, X, W, P, E, B, G, F, J, Q, N, M, U. Remember, U is U here. You see, small u is mapped to capital U and capital U is mapped to small u because it's the same thing. S, K, A, E, I. Right? So this is a permutation pi, which is applied to the alphabets. This is inverse permutation. So now I will ask you as an exercise, decrypt. Decryption it is given as M, G, Z, V, Y, Z, L, G, H, C, M, H, J, M, Y, X, S, S, F, M, N, H, A, H, Y, C, D, L, M, H, A. So again, this is an exercise for you. Now, one thing, so I think this you can do it easily. It's not a difficult thing. So capital M will go, for example, what? Capital M will be small t, right? And then capital G will be small h, and so on, right? So I hope it's not difficult for you. Please decrypt it as an exercise. Now the question that I'm going to ask you, note, I would say I'm going to put it as a note. How many keys are possible? So a key for the cipher permutation for this cipher permutation is all this 26 number. We need to try all permutations, right? Which is 26 factorial, right? If I want to find out the key, and which is bigger than 4 into 10 raised to 26, a very large number. Therefore, exhaustive key search is infeasible here. So substitution cipher is strong cipher. It's very good cipher actually. Okay. So I think I will stop at this point, and then we'll do few more things in the next class. Any question at this point? Please ask. Unmute yourself and ask. Any question?
Hello, sir.
Okay. Yes, please.
So, sir, if substitution cipher means if EKS is infeasible here, and we can see that the number of permutations are very large, then why did this not stay prevalent for a long time? Means why use of AES and
Oh, okay. So basically, you see, it depends on the kind of applications you are doing and kind of other things, and you will see that all this is classical cryptography, because you see these things, some of these things are still valid, so we can, for academic purpose, it is fine. but people have found different ways and doing other things and so on, right? Few things, even if EKS is infeasible, but sometime, it is impractical to use it, So what happens, for example, in these days, we use ASCII encoding. We don't do this kind of alphabet thing, right? So it all depends, because things have evolved since then. This is pretty old thing, okay? But of course, you are right. The substitution cipher is a strong one, and you will see that actually many other ciphers are a special case of substitution cipher, okay? But people have designed other ciphers also, which are, sometime, if I want to do it by hand, it is a difficult task, right? But maybe with a computer or sophisticated computers, we may able to break it, right? So it all depends on evolving and so on and so forth, many things. Sometimes it is very difficult to even break for the computer is still, the practical use may not be there, okay?
Yes, sir. Yeah.
Okay. Okay, so I think that's all for today. We will meet in the next class on